Oops. Okay. Yeah, so with that, the only difference, 5-step procedure doesn't change. The logic doesn't change. The only thing that changes is in step 3. Just because we got 2 populations, 2 samples, so the calculation will change. But we will still have the scenario when we know population standard deviation, when we don't know population standard deviation, or when we want to figure out the proportion. So those 3 will be quite similar. There is one additional topic that chapter 9 didn't touch. So I will spend a little more time with just a little more detail on the last topic. But the first 3 will be really quick. So we've reviewed the types of hypotheses, right? Your alternative hypothesis will either be not equal to or greater than or less than, right? So that makes the 2-tail test or the 1-tail test. The upper tail is greater than, lower tail is less than. So you can express it in the way to be mu1 less than mu2, or you can say mu1 minus mu2 is less than 0. And the above and the below, those 2 expressions mean the same. So it doesn't matter which one you write. So that's how we formulate hypotheses with 2 populations. And then in the scenario where we know population standard deviation, the test statistical calculation changes a little bit, even though the exact calculation changes. I wanted to explain that the structure does not change, because the z-score calculation, right, has been sample minus population, right, divided by standard error, which is your deviation. So in this z-score calculation, we still use the same structure. We capture what's in the sample and we compare what's in the population. That stays in the numerator. Then in the denominator, we put together the 2 samples to make sure we capture the variances, the variability in the data set. So it's the same logic. Why it writes different? So last time it was simply sample mean minus population mean, right, divided by standard error. Today, when we got 2 samples, what we are doing is the difference between sample mean compared to the difference of population mean. So that's what we are comparing. Not the exact mean, but the difference between 2 means. That's the numerator. Denominator, simply because we got 2 groups of numbers, right? And the standard deviation used to be the standard error used to be standard deviation squared divided by sample size. So now we simply put together what's from sample 1, right? The sigma 1 squared over n1, and what's from sample 2. So that's the sigma 2 squared over n2. So the denominator captures the variability when we put together the 2 data sets. It's how we smooth and blend everything together. But the numerator, like the difference in sample minus the hypothesized difference in population. Sample mean is going to be what we observe, right? X bar 1 and X bar 2 will be given, will be what we simply see in the sample. The hypothesized difference in population, this needs to be tied to the fundamental assumption that, right, non-hypothesis indicates no difference, no change, everything to be the same. So with that fundamental assumption, the hypothesized difference in population always equal to 0. When we write D sub 0 here, it's to indicate that we are comparing it with a hypersized population, with a hypersized population mean difference. But practically, this number always equal to 0. So when you do your calculation, you really don't have to worry about this number. You only worry two numbers in your numerator, just your x bar 1 and x bar 2. You take the difference of those. So do we have any questions here in terms of how to understand this z-score calculation?
I have an understanding. I would just be curious, kind of just when would that be other than 0? It's probably like upper level statistics classes, but I'd just be curious.
Yeah, thank you for asking. Very, very rare situation. If it's not 0, it will be specified very clearly. Like usually, right, the two classes or the 2 months of temperature have this level of difference, and then you compare with that expectation. So that needs to be specified clearly. If it's not specified, then the fundamental assumption is, right, everything is the same, no difference, no surprise. So that's what's behind the fundamental assumption of hypothesis test.
Okay, thank you.
Yeah, sure. Yeah, that applies for the mean and the proportion comparison. So yeah, the whatever difference from the population is usually always like 99.99% of the chance it equals 0. Other questions? Now we're good?
Yeah, we're good.
Okay, good, thank you. So yeah, so that's really the only difference, a different calculation of z-score in step 3. So just to quickly go over, sorry, like I said, I'm not feeling too well, so I'm just trying to quickly go over. Here we're comparing two companies' golf ball. One company is claiming that its golf ball rolls for a longer distance with alpha equals 0.01. And if we have all the information on sample size, right, N1, N2, sample mean, x bar 1, x bar 2, and the population standard deviation, sigma 1 and sigma 2. So when we have all that given, hypothesis formulation will be quite similar to what we learned before. Significance level is always given. And then when we get to step 3, just plug in the numbers in the formula. So numerator is always the sample mean comparison. Hypersized population mean difference is always 0. And then just put together population standard deviation and sample size from the two groups of numbers. Then we got our z-score. The one thing that I don't know if you have noticed is sometimes when you calculated your z-score, you don't even need to look up your z-table because your z-table stops at z equals 3, right, or negative 3. And you know that that's how many standard deviations you are away from the center. So usually if it's beyond like 2.5 or beyond the 3 standard deviations, it's almost guaranteed that you enter the rejection region because that's too many standard deviations away from the mean, right? That means you are going into an extreme value, extremely large value or extremely small value. That's simply different from the center. And when that happens, the natural reaction is you get to reject the null hypothesis because what you calculated deviates too far from your expectation. So as you practice, right, if you get a z-score equals 6 point something, you don't even see it in your z table. So you know it goes too far from the center. So you easily reject the null hypothesis. Of course, you can use a critical value approach to check. You can see, okay, if I have a one tail, right? If I have an upper tail test with alpha equals 0.01, leaving 0.01 in the tail, leaving 0.99 on the left-hand side, what is the critical value? Z equals 2.33. That's the threshold that separates your rejection region in the right tail and the non-rejection region in the left tail. And now your test statistic, 6.49, clearly goes beyond that threshold, right? So when it goes beyond, it enters the rejection region. So we reject the null hypothesis and we suggest the alternative, which indicates greater than, right, provides longer distance. So that's, yeah, same critical value approach. Or if you want to use p-value approach, you won't find it in your z table, but you will see in the z table when z equals 3, p-value is already very, very small, and it must be less than alpha. And that's all you need to know. If your p-value is smaller than alpha, reject the null hypothesis. So we reach the same conclusion regardless. So that's how we use hypothesis testing for two populations. Step 1, 2, 4, and 5 are the same. The only difference is step 3, using a different formula. So any question here? No questions? And then, I mean, besides this question, do practice afterwards. I give you another exercise on slide 19 for you to practice on your own to identify, right? Identify what's your alpha, what's x bar 1, what is x bar 2, what is n1, n2, sigma 1, sigma 2. Once you identify all the components, then it will be quite simple, straightforward to plug in your z-score calculation. And then critical value approach, p-value approach, either way, reach the same conclusion. So that's for population standard deviation known situation, right? The most standard situation.
Professor?
Yeah.
And it matters in what order you place your sigmas and your means, right? Like when you're going to subtract them. Like for example, x1 minus x2, I mean mean, sample mean 1 minus sample mean 2. Like it'll make a difference, or I mean it'll still show up at the extreme point, right, of the curve, so you would still reject the null or not. But
yeah, so it is not going to make a huge difference. Because you will have to identify your sample 1 and sample 2, right? If your sample 1, if you swap your sample 1 and sample 2, right? If you do this, then your z will simply have a negative sign. But when you swap, your hypothesis will also swap, right? So if you are expecting mu1 to be greater than mu2, if that's how I identified sample 1, sample 2, but you swap that, you're saying, okay, my class 2 is mu1, my class 1 is mu2. You swap that, then your expectation is the reverse, and your null hypothesis is also going to be reverse. So you will reach the same conclusion.
thank you.
Yeah. Yeah, so that's for the population standard deviation known situation. For the unknown situation, same as always, if we don't know sigma, we simply need to use sample standard deviation S to replace sigma, right? So the structure remains the same, still difference in sample mean minus the difference in population mean, then divided by standard error, but that's calculated from sample standard deviation. And then instead of Z, now we're using T to do the calculation. So that's quite similar to what we learned before. So one additional item is now, because we got two samples of different size and of different standard deviation, when we blend them together, we want the degrees of freedom to be capturing the two samples. It is an inconvenient calculation for degrees of freedom. I admit that it's quite some calculation. But the good news is you don't have to worry too much about how precise this number is. You are likely to end up with like a decimal place. So when you have a decimal place, you simply round it to the nearest whole number you have in your T table. Let's say if your degrees of freedom is calculated to be 61.85, well, that's not on your T table. You probably have a 60 in your T table, so you can round it to 60. And you probably will have a 70 in your T table. If you want to round it to 70, that also works. So at this level of calculation, that tiny difference doesn't change your conclusion. And remember, in my homework setting, I give you a pretty generous buffer zone. So that level of difference will still make you inside the buffer zone. So as long as you still reach the right conclusion, right, reject or not to reject the non-hypothesis, this like a rounding up or down a few degrees of freedom is now going to change that. It's now going to change which column or which levels of critical value it is. So don't worry about it. Then that's all I want you to know. There is this formula, and the reason why we do it is to blend the two groups of numbers and not to have any bias on the two groups. But with that, everything else is the same as what we learned in chapter 9. So let's look at the example. If we want to compare miles per gallon between two groups of cars, M car and J car, we can have sample size, sample mean, sample standard deviation. And then once we formulate hypotheses and identify significance level, same as before, calculate test the statistic in step 3, and just to make sure that you know it is T. And how you know it is T, when the question tells you it is a sample standard deviation, or simply when the question tells you sample standard deviation, or simply when the question doesn't tell you population standard deviation, that's when you use the T formula, because you are using sample standard deviation. And then similar to earlier, if you've done this practice enough, you can also guess that this is also pretty large T value, right? It also means quite some standard deviation away from the center. So it's likely to be a rejection again. And then you can look up that if you use critical value approach, calculate degrees of freedom, figure out which column, right? For a one-tail test, alpha equals 0.05, figure out a critical value 1.683, and our test statistic goes beyond the critical value, then it naturally enters the rejection region. So then we naturally reject the null hypothesis and we recommend the alternative. Or p-value approach, right, will lead us to the same conclusion. So that's for sigma unknown situation. Just to remember, instead of z, we are using t. So that's the second scenario. Third scenario is for population proportion. And sorry, and I'm also giving you exercise in the lecture note. So please make sure you practice. And then third scenario is to figure out proportion. So formula is the same, right? Z equals, in the numerator, we capture the difference in proportion. And then in the denominator, we capture, again, the joint deviation, right? The standard error. So proportion also uses a different calculation. We will need to first calculate the weighted proportion. So this is the same as how we calculate the weighted mean. So that goes back to week 3. Lecture note number 3, when we learned the basic concepts of mean, standard deviation, all that. So the calculation of weighted mean is captured in that week's lecture note. If you forgot, please go back. But it's really that your x value multiplied by the weight. And in this case, the weight is sample size, right? If you got a larger sample, it carries more weights. If you got a small sample, it carries less weights. So sample size multiplied by proportion of, right, each sample, and then divided by the sum of sample size, because that's the sum of the weights. So we got our weighted proportion, and that goes in the denominator, right? Proportion times 1 minus proportion, then multiply by the 1 over sample size. So denominator still captures standard error, while the numerator still captures the difference between the two samples. And again, compare with the hypothesized difference from the population, which is usually 0. So that's what we got. And then, sorry. So if we have an example here, we just got to capture the exact proportion, the sample size, and significance level. So step 1 will be to calculate the weighted proportion from sample size and the proportion from each one. Then this number, you see, that will be part of the denominator, right, as the weighted proportion. Then you see sample size, and then you see difference in sample proportion in numerator. Then everything else is the same. So just a different calculation of z-score. That is for proportion. Any questions on like those scenarios that matches with what we learned in chapter 9? No question, I hope. Okay, we're good.
So that's the equation, right, for the test statistic of population, right?
Yeah, yeah, test statistic.
And that, what does that tell us? The difference, or the what would that determine if they're different? If they are.
You mean this?
Yeah, like what is it? Like what is the test for? Like what is it telling us?
Well, that's the same as the test statistic you learned in chapter 9, right? So that's the number you will need to compare with the critical value, or that's the number you get to translate into p-value.
Okay, it's according to what the word problem is, right?
Right. Yeah. So remember, again, if we don't think about chapter 10, if you don't look at this complicated formula, do you still remember what was step 3 in chapter 9?
Right, to get the test statistic.
Yes, so it's the same step, calculate test statistic. And do you remember after that, what did we do in chapter 9?
The test that followed? I mean, the part of resolving the problem, rejecting the null or keeping the null?
Yeah, it's the same procedure. You are calculating, so you are calculating the same test statistic.
Got it. Yeah.
Yeah. Everything else is the same.
Thank you.
I guess the only thing that we're doing now is that we're just merging 2 populations together and averaging.
Yeah, exactly. The only difference is now we got 2 groups of numbers. So we are blending them together. So that's why we got a different formula. But the logic and the procedure is exactly the same. The test statistic is the same test statistic that we learned in the last chapter. The critical value approach and the p-value approach are exactly the same. So those are like really a repetition of what we learned before. But I do want to spend a little time on this new topic. So when we have 2 populations, and then obviously 2 samples, right? Sample 1 from population 1, and sample 2 from population 2. We can actually have matched sample. So this mostly is used in situation when we have to compare experiment result. Usually we compare before and after, right? Before a new medicine, right? Before the patient takes a new medicine and after they take the medicine, or before students use a new test preparation study guide, and after that, right? Do they have different performance? So it's usually used to compare before and after. A typical example, well, and the reason why, the reason is we need to be able to match every single individual in the sample between the first group of number and the second group of number. So in other words, your sample 1 and sample 2 needs to be of exactly the same size. If you have 30 observations in sample 1, you must have 30 in sample 2. That's the only way you do a 1-to-1 matching. If you have 15 numbers in sample 1, then you must have 15 numbers in sample 2. And you must be able to match like 1-to-1. If you are not able to do a matching, then you can't use this method. So that makes it quite limited. But I give you an example when we could do the matching. So again, if a new medicine is invented and the new medicine is supposed to decrease blood pressure, so we wanted to test, is the new medicine effective, right? Does it actually reduce blood pressure? So we can collect a group of 30 patients, right? Patient number 1, test his blood pressure before he takes the medicine and measures it after he takes the medicine, right? And then for patient number 2, we measure her blood pressure before the medicine and after the medicine, right? Patient number 3, blood pressure before and after. So for the 30 patients, we easily get the 2 groups of numbers, right? Before and after. And we can do the precise matching, right? From patient 1, that's before and after. Patient 2, before, after. Patient 3. So we can do the matching without any confusion. You can't match patient 1 with like patient 10, right? That's not comparable. it has to be patient 1 before and after. So as we are able to do the matching, we also focus on the difference. So we will be looking at, right, okay, before and after, what's the difference? Maybe for patient 1, it dropped by 10. For patient 2, it dropped by 20. For patient 3, it dropped by 0, right? So we can do that for all 30 patients. So the key is the difference at the individual level, not at the group level. And then we just look at that new column of difference, calculate the mean, the standard deviation, and do the comparison. So that's the process of analyzing matched sample. And like I said, the prerequisite is you get to have 2 samples of exactly the same size and probably even the exact same like individual or object that I can do a precise matching. If you can't do a precise matching, if you were like, oh, the first number in sample 1, should I map it with the first number or should I map it with the second number? If you have that level of confusion, it means it's not a matching sample, and you can't use this method. It needs to be very clear. Just match 1, 2, 3, 4 every single observation. And with that difference at individual level, then we calculate test statistic T to be the average, right, the mean of that difference divided by the standard deviation of that difference over square root sample size. So that's the test statistic in matched sample. So it's not captured at the group level, but it's captured at the individual level, then put together. So let's look at one example here. How do we do the matching in this one? Sorry. So here in this example, we wanted to deliver documents from a company's headquarters to its different offices. And we want to compare 2 delivery companies to see if the delivery time are the same or the different. And we can do the matching by giving the same target. So the first observation is to deliver the documents from headquarters to their Seattle office. The one delivery company takes 32 hours, but the other doing the same task only takes 25 hours. So there's a difference of 7 hours. To deliver to their LA office, right, from headquarters, the delivery time for the first company is 30 hours, and for the second company is 24 hours. So we can do the exact comparison. So that's a difference of 6 hours. If they get to deliver to the Boston office, it takes the first company 19 hours, but the second company only 15 hours. So that's a difference of 4 hours. And so we can do this comparison at the individual level, the individual observation level. So then the area of focus is the last column, the difference at individual observation level. So now we got 10 numbers of differences. What we do is we calculate the mean of the differences right? Put the 10 numbers together, divided by 10, and we see, okay, the mean difference is 2.7. Now we calculate standard deviation of the 10 numbers, 2.9, and then calculate test statistic, right? So now it's the mean difference divided by standard deviation of difference over square root sample size. We got our test statistic, and the easy part of this test statistic is our two samples are of the same size. So we actually do not need to blend them. They are the same size and they vary in the same manner. So degrees of freedom goes back to n-1. So when we have 10 numbers in the sample, degrees of freedom is simply 9. So from there, and knowing alpha, it then becomes straightforward to figure out the critical value. Then same as every other question, when we use critical value approach, compare test statistic from step 3 with the critical value we calculate in step 4, and then decide whether to reject. So that's what we do with matched sample. It doesn't happen all the time. It's quite limited, only when you are able to do the exact matching. And sometimes, here I got to another exercise. Sometimes the question will make it even simpler to save your time calculating the mean and the standard deviation for the differences. The question will even calculate the mean in difference and the standard deviation of the difference. And then all you need to do is to plug in the number in the T formula and get your test statistic. Then again, if you see it's a huge value, you know it goes beyond the critical value. You know it goes into the rejection rate. So that's the only new concept in chapter 10, this matched sample. So wanted to see if anyone has question in matched sample.
I'm just gonna watch the videos that you have up and just let it settle down, to be honest.
Or anything like doesn't make sense for you now.
I mean, the only thing I would ask is you're okay with us using Excel for a lot of like the standard deviation calculations as well?
Yeah.
Okay.
Yeah. Other questions? Yeah, okay. So that's really the only new topic. Okay, no question. Yeah. Okay. Yeah, sorry about today. I'm just not feeling too well, so just rushing through the material. Raining hard. Yeah. Yeah, it's a type of weather gets people sick. So yeah, just take care of yourself. Yeah, and like I said, chapter 10 quite similar to chapter 9. For the 3 scenarios that we've seen. All that's different is step 3. We got a different formula to calculate test statistic. And the new concept is the matched sample. At matched sample scenario, we capture the differences at individual observation level, not at group level. So that's all for chapter 10. And we have homework for this week. And then the exam for next week, just covering the 2 chapters, 9 and 10. I saw actually 2 students already completed homework for this chapter. And when you're already done with that, that means you already got a good understanding of hypothesis testing. And just do a little review and you should be ready for next week. Any last minute questions before we end? Are we good?
Yes, I'm good. Get well, Professor. Hope you get
Yeah.
some really good medicine inside you and some good rest.
Thank you. Yeah, thank you. I appreciate that.
And good luck, class.
Yeah, thank you. Okay, good. Good. Yeah. Thank you for your understanding. Yeah. If you got any question, email me, or we can try to meet during my office hour. I definitely want to help and get you prepared for the exam. But yeah, thank you everyone for today. And good luck next week. I will see you in 2 weeks then. Bye everyone.